Hi everyone, welcome to the Applied Research Symposium at City University of Seattle for the Spring 2025. I am Honorine Domza and I will be chairing this session. So for the presenters today, we have presenter 1, Fernando Mackenzie, presenter 2, Indanzip Kaur Rato, presenter 3, Kairat Bet Zafran Bevkov. So we are going to, each presenter is having 50 minutes for the presentation and 5 minutes for Q&A. So we are going to start with the first presenter, which is Fernando Mackenzie. So you have 50 minutes to present, Fernando, and 5 minutes for your Q&A. And I think you'll be presenting on disinformation decoded, a cloud-native pipeline for analyzing through driving on decision-making.
Yeah.
So,
Let me share my screen.
okay.
One second, guys. 1 second. I'm trying to get this. Okay, so
Okay.
all right. Can you guys see my screen?
Yes, we can.
Okay. All right. Good afternoon. Good evening, everybody. My name is Fernando McKenzie. My capstone project is Disinformation Decoded, the cloud native pipeline for analyzing troll-driven influence and decision making. I'll say this one was one of my hardest projects. The agenda, it's the problem statement, the motivation, the background, the related work, the approach, the design, the implementation, the data connection and analysis, the findings, conclusions, and then future work. So the problem statement for this capstone was, how can we defend decision making when disinformation campaigns are designed to emotionally manipulate and cognitively mislead? The motivation is understanding how disinformation alters decision makings is critical online campaigns, increasing manipulative emotion and perceptions at scale. So before I get started in this, I just want you guys to think about infrastructure as code or provisioning code from your terminal to the cloud for it to populate, for it to do what you need it to do. So for the background, we use all of AWS SDKs, the SC3s, the Lambdas, the Glue, the SageMaker, for us to be able to put this project together. So the core AWS servers used through the pipelines and their specific roles, which is the Amazon S3 services, which is the central data lake for processing outputs in a scalable partition format. The AWS Lambda is orchestrates the workflow by triggering the glue based on the S3 upload. The AWS glue then handles the transformation process, cleaning, validating, and formatting tweets between the analysis. The Amazon SageMaker holds the sentiment analysis mode used to scoring each tweet. Then the DynamoDB stores each embeddings and metadata and supports the semantic quality and detection, while the Amazon QuickSight provides the interface, visualization, sentiment trends, and metrics. All these services will deploy and are measured to the Terraform, so terraforming in Python. The related work. So first we have DISCO, which is the disinformation identification by semantic co-occurrence, which uses graph modelings and semantic scores to detect misleading context, offering high accuracy, strong explainability through its suitable batch analysis. The second we have is SIMID, which is similarity-based misinformation detection. which is focused on semantic similarity, which users communicate using the SBERT embeddings. SBERT, which is the sentiment bidirectional encoder representation from transformers. It'll perform but lacks real-time capability and that requires orchestration. Lastly, social net diffusion analyzes how misinformation appears in networks. It is scalable, interpretable, and works with serverless pipelines. The approach, the core AWS services uses our pipelines and how we deploy them using infrastructure as code. We use Terraform paired with Python to define and automate the deployments of everything. S3 for storage, Lambda for orchestration, Glue for data transformation, SageMaker for modeling, and QuickSight for analytics. Each resource was provisioned to users using a modular template to ensure consistency, scalability, and repeatability across the entire system. This allowed us to move from raw data up to structure insight with minimal manual setup and automation and full automation. So the implementation, this slide outlines the implementation phase of the project where the infrastructure and pipeline components were built and deployed. Python was used along with the AWS CDK and Botto 3 library to automate the infrastructure deployments while the slide mentions AWS CDK. The actual implementation was managed using the Terraform, which provisioned all the cloud services through the infrastructure as code. This includes the S3 buckets for raw processing, the Glue ETL job for pre-processing, the Lambda function for orchestration, and DynamoDB for metadata tracking. The goal is to create a modular, scalable system capable of handling real-time batch processing. And then the optional SageMaker models were also configured for sentiment inference, allowing us to plug in advanced machine learning when needed. This automated deployment ensured the repeatability and consistency. The design. So here, as you can see, the orchestration piece is the Lambda function with the pre-processing triggering function, which indicates the pipeline that a new tweet data has been uploaded. So it triggers a downstream Glue SageMaker. Sorry. So the Glue SageMaker components to automatically enable end-to-end automation, the ETL storage, which is the AWS Glue process to clean the tweets and process the tweet data bucket, then update the structured data that is ready for inference, process embedding and metadata and stored in a DynamoDB embedding table. So the sentiment inference of this part is a SageMaker model, which is the endpoint, and it runs on sentiment analysis on clean tweet text, the model configuration, and is managed through the sentiment analysis endpoint configuration, which is enabling continuous scoring and inference. So for the data collection piece, we have a little bit over 3 million tweets across 9 CSV, which is publicly available on Kaggle. So we uploaded all these CSV into the S3, and then we pre-process these tweets using the Glue for cleaning, normalization, and tokenization. For the data analysis, the model evaluation and reporting components of this pipeline, the code you see is part of the function to consolidate and format model performance and metrics. After training the sentiment model, a structure way to compare them was needed. This function extracts key metrics and functionality, precision, recall, difference from F1 scores to macros, weight, and micro. It also includes more advanced evaluations such as the Matthew correlation coefficients and the Cohen's kappa, which are useful when dealing with class imbalance as well as cross-validation statistics to ensure each metric is formatted to the 4 decimal places. It is to ensure consistent and readability. The results are collected into a panel data frame, which then makes it easy to export the metric table, including them in reports or visualization tools like QuickSight, Excel, or Power BI. So the findings, the key results and performance insights from this full pipeline executions, we verified that our injection process from the S3 to Lambda and Glue was highly efficient across 3 million tweets. We split it into multiple CSV files. Each file was ingested clean, process under 2 minutes, confirming that the pipeline can handle high data volumes and low latency. On the machine learning side, logistic regression was performed very well. It achieved 95.1% accuracy with the F1 score of 89.5, and it completed training and cross-validation successfully. We also tested the random forest model, which reached an even higher accuracy of 96.1 and macro F1 score of 92. However, cross-validation for that model took over 9 hours and was never completing, indicating performance trade-off for more complex classifiers. So finally, the sentiment inference is handled in real time using SageMaker predictions and generated with an average latency of under 300 milliseconds per tweet. This makes it suitable for use in live monitoring and rapid decision-making scenarios. These results demonstrate the pipeline scalability, modeling accuracy, and readiness for real-world applications. So here's my demo, everybody.
Are you talking or is it playing? I can't hear you.
Is that you guys can't hear it?
Is anyone hearing what is coming from the recording?
Is anybody else having an issue here in the recording?
Jeff?
Yeah, I'm not hearing it. No.
You're not hearing it? Okay, so if you can't hear it, I don't know. Let me see. Microphone. Okay, since you can't hear it, I guess I could just do it live. Can you guys see my screen? Did it switch over to the terminal?
Yes.
Okay, so basically what I wanted to show you guys was, so this is the training model. So for the training module, we created a class, which is the sentiment trainer. So the sentiment trainer creates the model for logistic regression, random forest, SVM, 90 So these are the models that we'll be testing again. So then we'll load the files. After we load the files, we process them. We create a sentiment label after they're processed so they can be greater identified. Here's some of the labelings, and then preparing the features and vectorizing the text, calculating comprehensive metrics, which is the same, the accuracy, the balance, the precision, the recall, the F1 macro, matching correlation, and the core and kappa with the rock score at the end. So that on this one, we have what the data set will look like on the inside once it's consumed, and then the evaluation of the model. This is what if I can get it to click. This is what the architecture looks like from this level, from Terraform. So you have the DynamoDB table that was created, and then the Lambda function. Once the Lambda function is instantiated, it calls out the S3 bucket, then the glue job, then the SageMaker for ML training, and then the dashboard. The dashboard is not done. Then you'll see quick site with all of its properties. Once everything is ran, then we get this comprehensive report that tells us how we scored and what was built. So what was built is here. So we have the buckets, the model, the tables, the Lambda function, the glue job, and the SageMaker. All of these were created and ready. Minus the quick site, we use Python 3.9. Here it talks about the training systems and the component for the full training. The performance was limited because we did deploy it locally. So locally, it took more than 10 hours. And once I loaded it into the cloud and did like a fast version of it, it took like 15 to 30 minutes because the original version was 2.9 million tweets versus the second version, which is the shorter sample. That was 900,000 tweets with only 3 folds. That also explained that in the reporting. So they tell you here that the logistic regression took anywhere between 2 to 5 minutes, and they anywhere between 1 to 3 minutes, and the random forest took anywhere in between 8 to 15 minutes. So the full model over 6+ hours, and then this one was faster, between 10 to 15, 20 minutes. The logistic regressions or the comparisons, the random forest did a little bit better on the second time, coming up with the 96.1 accuracy, and then the logistic regression came out at 95. And then you have the F1 scores for both of them. Like I said, I couldn't finish because of time constraints and cost. Every time you run these models on AWS, they cost a little bit. So I only ran it twice. So the files that were generated, you could be able to see this here. And let me see if I'm still. So here are the file changes, or the files that were created inside of the S3 bucket. Then you'll be able to check your logs or what was created in CloudWatch from all the runs.
Fernando,
Hello?
you just reached your 50 minutes.
I did?
Yeah. I sent you,
Okay.
a text through Teams. You can check. Okay, thank you for presenting. And yeah, we move to Q&A. Any question?
Quick question, Fernando. First of all, great job. So what was kind of the basis of the criteria whether something was disinformation or not? Do you have like models that would do that?
Somebody cut in at the end. I'm sorry. I missed that.
Oh, okay. I was just wondering if your criteria for what was something's misinformation or not, did you have certain models that you kind of looked at for that kind of data?
Yeah, so I looked at, what was it? 4 different models. They were, let me see. So the accuracy, the F1, the precision, the recall, Matthews correlation, Cohen kappa, and the balance accuracy for the model comparison. And so it was The algorithm types were linear, ensemble, kernel, and probabilistic.
Cool. Okay, thanks, man.
Okay. Thank you for your question, Jeff, and thank you for the answer, Fernando. Any other question? Okay, let me ask one question. How can you, like an organization or policymaker, use your findings?
How can an organization or who use my findings?
Policymakers use your findings to build like a more resilient system. How can they apply?
How can they apply my system? You just need the data, to be honest with you. Once you get the data, you clean the data, you'll be able to tell a better story with it. So for decision making, it just depends on what they're studying. So if they're studying customer churn data, you'll be able to see with different models, not the ones that I use, you'll be able to see different metrics, and you'll be able to squeeze out the numbers depending on how many times you train it or validate it. So anybody can use it. It's not one fit all mold, which is the cool thing because for this particular use case, I use disinformation and how you can use disinformation to make better decisions. Because like these were the tweets that were used for the 2016 election to meddle with the 2016 election. So if people could use something like this to be better informed or make better executive decisions based on what the model is trained, then I think that would be the
Okay.
better use.
Yeah, okay, thank you.
Mm-hmm.
Okay, I think if there's no more a question, we have to move to the second presenter, who is Indanzip Kaur Rathore. She's presenting on a cloud-powered deep learning mechanism for analyzing natural disasters.
Yes.
Okay, you can start your presentation, Indanzip.
Is my screen is shareable?
Yes.
Thank you. Hello everyone, my name is Indradeep Rathore. Today I'm excited to present my project, Cloud Powered Deep Learning Mechanism for Analyzing Natural Disaster. This research addresses rising flood risks using AI and satellite data. It aims to build an accurate, scalable, and explainable flood detection system. Now let's take a look at agenda for today's presentation. Problem statement. Current disaster systems are slow and now detailed, relying on manual reports and basic images. Can we make them more accurate and scalable? The goal is to use deep learning to process time-space data and explain results clearly for real use. Motivation. In the recent news of flood events have occurred in disaster-prone areas of Asian countries, and national authorities are advising locals to stay alert and safeguard themselves. Natural disasters harm many lives every year. AI and cloud tools now help analyze these events on a large scale. Background. Deep learning uses layered neural networks to learn complex patterns from large datasets, achieving top performance in tasks like image classification and disaster prediction. Cloud computing runs AI models like UNet fast and at scale, handling large map data, supporting quick disaster response even in low resource areas. spatiotemporal models algorithms that analyze data varying across space and time, crucial for understanding involving disasters. Explainable AI helps make black box AI models more transparent by using tools GradCam, Climb, and Sharp. This builds trust and supports faster decision during disaster. Multimodal integration involves combining different data types such as text, images, sensor data, and location information into a single deep learning model to improve disaster prediction. UNet variants, originally for biomedical image segmentation, are effective in flood or landslide mapping using improved skipped connections and deeper layers. Convolutional long short-term memory, especially beneficial in predicting the progression of disaster, such as wildfires or floods by learning patterns across space and time. Related work. The table compares multiple research efforts in the area of disaster prediction and management using deep learning, focusing on disaster types, deep learning techniques, data sources, and cloud deployment. This approach uses a multimodal deep learning pipeline. It combines satellite images with extra geospatial data like weather and terrain. The system uses vision language transformers and spatiotemporal models. This helps us deliver fast, clear, and interpretable disaster insights in near real time. As per our approach, it was quite evident to go for the flood data, as my own home country is India, where floods are quite common. In comparison to using CNN and GAN model, vision transformers along with fusion of CNN and LSTM seemed best fit. All the implementations was performed on AWS cloud with explainable AI integration for end-to-end monitoring and disaster alert mechanism. AWS architecture, data source input, satellite IoT sensors. AWS Open Data provide real-time data such as rainfall, soil moisture, and satellite images. API gateway connects external data sources to AWS. It allows secure API access to push data into the system for processing. The Amazon S3 stores raw data, clean data, and model results. AWS Lambda processes and cleans data automatically before model use. AWS SageMaker fetches data, trains model, explains results, and makes predictions. API Gateway second usage. API Gateway second usage triggers alerts or further actions based on model output. Amazon SNS sends alerts, email, SMS to emergency responders when a flood risk is detected. Amazon Cloud Watch monitors logs and systems, performs for Lambda, SageMaker, and other services. Emergency responders receive real-time notification and warnings to take quick action based on the prediction. Implementation. The system uses AWS to collect real-time satellite and sensor data, clean with it Lambda, and store it in S3. SageMaker trains flood prediction models and sends alerts via SNS. TensorFlow handles deep learning with data processing using pandas. Django Flask and React support visualization. Data collection. Satellites images were collected from Copernicus Open Access Hub. API helped download scenes based on location, time, and disaster type. The image from Copernicus shows a flood area in a marked box. It helps detect and monitor floods using satellite data. The crisis medic dataset from Amazon containing tweets and images was a secondary source. Disaster images. The table shows flood-related data like weather, river levels, and land type and population. It helps understand where floods happened and why, which supports building better flood prediction models using AI. Data analysis. Satellite images were used to track floods over time, brightness, cloud cover, and water bands help spot flooded areas. GeoPandas and AWS manage the data, cleaned data, trained models for accurate and flood detection. This bar chart shows images count for 5 natural disasters. Floods, 3,401 images in red are a key focus, while hurricanes have the most images, 4,517. It highlights data balance and helps plan deep learning training by avoiding bias and guiding pre-processing. The heat map and bar chart show how flood-related features like rainfall, elevation, and water level are related and distributed. Tools like GeoPandas, Seabonds, AWS, and Sentinel Radar help improve data accuracy and support better flood prediction. Findings, the data was 92% useful, but 67% had low damage, causing class imbalance. UNET gave strong results, IOU 0.92, DICE 0.96. Normalized difference water index had high flood correlation 0.83 and sharp value 0.34. AWS gave fast result 1.1 image per second. Conclusion, developed a deep learning flood monitoring system using high quality Sentinel satellite data. It was deployed on AWS, processing each image in about 1.1 second and improved water detection by 27% up to 48 hours before a flood. Future work includes combining satellite, weather, social media, and IoT data for better flood detection. A mobile web app will provide real-time alerts. Focus will also be on authentical, fair, and transparent deployment. This is my demo video of the AWS architecture. This is my AWS architecture for this satellite's imaginary-based flood detection and alert-based research. Now let's go through each phase of the architecture. Lambda created a function to pre-process raw data collected from satellite API gateway and other sensor-based IoT data stored at S3. SNS alert after data is processed. S3 created a bucket to store the raw data, processed data, trained model, and Python script. Data processing is done. Now coming to SageMaker phase. SageMaker, all the data model training, evaluation, metrics are done on SageMaker AI, and processed data is fed from S3. Then alerts are generated based on the model's predicted output. Last phase, alert mechanism. Lambda flood alert function is created to generate SNS alert. SNS notification service is being used in order to alert the emergency responders via SMS and email protocol, which is triggered through Lambda flood alert function. This is an example of SNS received over email and SMS. These are the references I used to support my capstone project. This is all from my side. If you have any questions, feel free to ask me. Thank you.
Thank you, Nancy, for your presentation. Any questions? Mackenzie? Fernando?
How did you like working with Amazon?
Yes, pardon, please.
How did you like working with Amazon?
Yes, I worked with Amazon. Yes. No, I'm not. I didn't work with Amazon. I just make my, I use Amazon services for my project.
Yeah, that's what I meant. Sorry.
Okay. Yes.
Yeah, so he's asking like using the services, right? How did you like working with it? Was it interesting working with the Amazon services and in your project?
Okay. Thank you.
No,
I like
Fernando.
these yes,
Okay.
I like these services because last time, according to my last classes, I learned AWS. So that's why I plan to use in my project.
Okay, that's awesome.
Thank you.
Any other question? Okay, let me ask my own.
Yeah.
How does your model ensure timely, accurate insights during like a natural disaster in case it doesn't have like complete data? Do you have any mechanism you set up for that?
Sorry, I can't understand your question.
Yeah, so I'm saying your model, right? How does it ensure timely and accurate insights during a natural disaster?
Yes, the data set, according to my findings, the data sets were 92% useful, and but 67% low damages causing. UNET gave strong results like using IOU and DICE 0.96 normalized difference water index, high correlations. So I think we can do more efforts, we can use more services to get correct data from the uh, uh, from uh, from from the result for the results.
So are you trying to say we can exploit the accuracy to do that? The accuracy you got from the training your model?
Yes. So I find out the accuracy. It's 92%. The images 92% clear. Then the other research. So I use CNNs uh, in my project. So
Okay.
these helps to make a clear pictures.
Okay. Any other question?
Thank you for sharing, Inderdeep. Good work. What was
Thank
the
you.
biggest challenge in carrying out this project?
Yes. Um, Actually, the most challenge was when I find out the data set for my project. So I didn't find, I'll take 1 week to find out my data set for this project. So when I was uploading the data set, it takes 8 hours. And so these things I have I feel very hard to download the data set in my project. And other things I also faced last year, I log in Amazon web service account. So that was expired. So I make a new account and then my services work.
Okay. So follow-up, thank you. Follow-up question. Were you how much did you need to pay for the Amazon services?
I just pay for 2 rupees, 2 rupees. But these are not too expensive. But the thing is, I get to make another account, and then one time the payment was denied. I don't know what's the issue was. So that's why these things are I faced during my project.
Okay. Thank you.
Okay, thank you for your presentation, Indanzi. We're going to
Thank you
move
so
to
much.
the third presenter, which is Kairat Berg Dafran Bekov. He's presenting on AI-powered conversational assistant for predictive job code estimation, and his app is called Estimate AI. So Kairat, welcome, and it's time for you to present.
Yeah. Hi everyone, my name is Kairat Pik, and today I want to talk about my capstone project, the Estimate AI. This is the AI-powered conversational assistant for predictive job for estimation. This my agenda is like a regular agenda. You start introduction, so and like continue. The introduction. So let's start with the core question behind Estimate AI. My question, like, how can small contractors reduce the cost and the time of giving quotes by using AI? So for small businesses, especially in home services like fencing, decks, or gates, quoting job usually requires like manual effort or like phone calls or site visits, and even when the customer might not accept the job. The Estimate AI offers like a solution by generating accurate and automated quotas directly from user input. Uh, so it's ended from clear says like manual quoting processes are costly and inefficient. AI data conversational systems could offer a faster and scalable alternative. So that idea is what inspired this project. Uh, Understand users' input and ask follow-up questions and deliver quote price of job motivation. So several studies confirm that there is AI, the power of AI is opportunity, and researchers like Abid and Miranda have shown that the machine learning models can predict construction costs faster and in a more accurate way. That means like small contractors could benefit from real-time quoting with fewer delays and more consistency. The, let's start with the continue with the background. The traditional quoting repair or installation job requires phone calls, emails, or even a visit to the site. So that can take hours. And if the customer says no, it's all waste of time. So my project Estimate AI changes is it uses NLP, natural language processing, to understand customers' message like in plain language, and after that, ML, machine learning, uses and like can predict job cost. So in this project, Estimate AI can work on browsers, uh, on any devices, so making it simple and user-friendly. So what about related works? So let's look at some similar reports. So I found like three. I use it, found and use it three authors. The first one, Albert et al. He used ML machine learning to predict job costs, but it wasn't real time and it needed like technical setup. What about Miranda? So Miranda used data for early planning, but it was built for analysis. And the handoff AI gives us instant pricing with simple UI, but doesn't allow contractor customization. So that was the third one. Handoff AI was like more for big construction, like if you like this style one room or like kitchen, uh, it can predict the price for that things. But my estimate AI is like uh, more like for like small jobs, but for small job. The power of SMI is like builds on those ideas from those three, the combined speed, accuracy, and the easy of use for everyday small business owners approach. So how does estimate AI work? So first, a user types a message like fix my wood fence urgently. Then my NLP Python model extracts scale like details of uh, like material urgency and job date. After that, uh, my bird based intent classifier confirm job types and like this it continues and if there's something missing like length or number of parts, the chatbot asks questions to get that info. So once everything is gathered, once once we get all of the data, so my ML random forest model works and we predict job price. So this code is sent over back to the user instantly uh, in clean and understandable format. My use case, a customer sends a quick message describing a broken wooden gate or something, and then assistant replies ask for missing info, and then after that provides an estimate price. So all in less than a minute. So no forms, no cost, no delays. Then system diagram. Uh, this system diagram shows how everything is connected. The front end is built in React, the backend uses Django, and they're in separate folders. You have ML like this NLP and the random forest deployment. So right now, like my project Estimate AI runs on two-tier architecture, the front end and the back end. In backend, I'm using these trained models in the backend. Right now, it's not separate because after I trained model, I put in backend and there my backend can use this trained ML. How I collected data. So, first, the data comes from two main sources. First one is like user's input, like install a certificate metal fence. Second one is CSV uploads. So I have like data sets. You can see like so deck repair, job type, and the material wood, length, parts, and urgency. And after that, the final cost. This one is like this one is data set, and first one is the user's input. Then my estimate AI stores like generated quotes, the final price. So right now the system focused on fans, deck, and gate jobs, three jobs. Where accurate pricing matters most. The intention is that all fields are collected and reflect real market prices. Then the assistant does a great job understanding input. It correctly detects urgency like 93% of the time. So my accuracy of my ML model is 93%. The estimate like extracts materials like wood and vinyl, then uh, can understand like with numbers also data like 10 and with words also like 10 tip, and they can understand also words like the synonyms. If user inputs like repair or fix, it can understand both of them. Price prediction. So mix my data analytics. So the trained model gives price predictions within use about $37. So this is my error. So for this, I'm using like between two prices to show like final predicted price. So the most important factors affecting the price area is like job length, type, and urgency. So this removes the need for costly site visits just to give a quote. The estimate AI finishes a quote session in just 44 seconds on average, so it avoids repeating itself and asks questions only when needed. So this makes it fast and smooth even on mobile devices because of website. The estimate AI helps small service businesses can understand user input clearly, predict price fast and accurately, save with a lot of money if you take a look to labor or fuel and the time. Uh, so it's ready to use tool that's lightweight, customizable, and scalable. The conclusion. To wrap up, the estimate AI is a conversation AI that makes coding easier, faster, and smarter. It understands messages, predict costs, and deliver quotes in under a minute, like in 44 seconds. And it helps contractors reduce wasted time and focus on real jobs. In future, I'm planning to create a separate ML tier. It will be a third tier in my project, front-end, backend, and ML. So it can with third tier I can create like new page for special for contractors, like contractor dashboard page where contractors can see customers input, customers request, and they can also like update upload their data sets like how I showed before earlier, like CSV file. And the next thing is like support more type jobs. Like I can also add like plumbing, painting, and embossing. So I hope those updates will make the system even more flexible and powerful for real world use. Let's see like demo. So so you can see right now is I'm going to run. So here you can see my client is my front end, server is my backend, and the model training is trained model. Uh,
Are you playing the audio or are you talking?
yeah, I'm playing video and also talking.
Because I can't hear anything from
Oh,
the video.
oh yeah, there's no audio for video, just video. That So right now I'm going to run my front end. So I already run at my back end. So let's see. This one is contractor's website. One of them is TotalFix, and if you're like a chatbot, it just asks like, I'm asking like hello, and it's asking like what kind of job is this? Like I'm writing like hands repair, and after that it asks about material. So I like this vinyl, then length, and then parts and urgency. If I write wrong word, it can re-ask. But here you can see that thanks for based on what you told me, job fence repair, material vinyl, length 10 feet, parts 10, and urgency is just standard. And so estimated price is 431, and between 431 and 458. This is my result, what I have done. Yeah, in my references. Yeah, thanks so much.
Okay, Karabek, thank you so much for your presentation. Any question from anyone? Okay, Veronica.
Yeah, I have a question. I was curious how you went about choosing BERT as for intent detection in your system versus any other tools.
Yeah, I use it two NLP. First one is BERT, and second one is Spacey. So first one is why I use it BERT. So when user inputs like bunch of text, the BERT is one of like powerful NLP which can understand user's intention. Like if you write like I want to repair fence or I want to fix my fence, the bird can easily understand the intent of customer, and they can take like intent or opinion of customer, like can extract the idea of like to repair fence despite of yeah. So
I know
bird
you
is,
mentioned two of them. Did you consider any of the GPT-based models?
oh yeah. So my project is like for small contractors, and I thought that then LLM is the power of NLP will be more efficient. I thought like this, yeah.
Yeah, okay. I just curious. Thanks.
Yeah.
Okay, thank you for your question, Veronica. I have a question. So how do you handle jobs that don't fit any previous data? Or if you don't do that now, how do you plan on handling that?
If you don't have any like job types or anything, so you cannot answer for this thing, like my estimate, I cannot answer. But in the future, I thought in my future works, I can add more job types. I think so. This is for special for contractors, small contractors, and it can only work with several type of jobs.
Oh, okay. Okay. Okay, like the scope is limited for now. Okay.
Yeah.
Okay. Okay. Thank you so much for your presentation, and thank you to everyone. Fernando, Indandip, and Karadek, thank you for your presentation. I think with that, we are going to end here. Good luck in your continuation and pursuit of your career, and congratulations.
Thank you so much.
Thanks so much.
Thank you
Bye.
guys.
Thank you.
Take care. Bye-bye.
Bye.
Bye.